Hi, Physics 2011 students. What we're going to get into in this video is talk about some of the definitions that we need uh, to understand before we'll be able to work with energy conservation. And we'll also talk a little bit about how what we're doing now connects with what we were doing in the last chapter. So before we get into chapter 8, the current chapter that we're working on, where are we coming from? Well, we're coming from chapter 7. It's about work. And we spent much of that chapter building up our mathematical tools to allow us to compute work. And we looked at different definitions of this. We called it FD cosine theta, and we called it F dot D. Um, and really, if the force isn't constant, the most kind of general definition of this would be that work would become an integral between a varying force and a displacement. And so like I said, we spent much of the chapter working on mathematical tools, uh, integration principally, and the dot product, this vector mathematical operation. And then in the last section of chapter 7, we talked about the work kinetic energy theorem, which tells us that the net work is equal to the change in kinetic energy. And this allowed us, this would allow us to kind of connect this work picture, which is fundamentally depends on forces, to energy. And energy is what we're going to be talking about in chapter 8, energy conservation. And so kinetic energy, the energy associated with motion, we're going to build onto that potential energy, the energy that's associated with a configuration or with a position. And all of these things, work and these different kinds of energy, have units of joules. And yeah, so this is kind of basically where we're coming from. We talked about work, and in the last section of the previous chapter, we had looked at kinetic energy and the work kinetic energy theorem. So now we're in chapter 8, energy conservation. You'll notice chapter 8 has a lot more sections than chapter 7. It's going to take us a little bit longer to get through this chapter, but this is going to build directly on what we were doing. So the first thing that we need to talk about is a distinction between kinds of forces, and this is necessary for us to be able to define potential energy. So the first thing that we're going to do is distinguish between types of forces. And the two types of forces that you have are conservative forces and non-conservative forces. So let me plop a definition in here from your text. So a force is conservative if the work done by that force on an object, moving it from one place to another, depends only on the initial and final positions of the object and is independent of the particular path. So, and I'll focus here on independent of path as being kind of the key idea. So, probably our most important example is gravity. So our key example is gravity. So, consider like lifting an object or something, a particle here. You could lift it straight up, some height, or you could lift that particle, it could take some weird, like meandering path to that height. Or, maybe you could take a path that's diagonal to that height. We know, based on what we did in the last chapter, gravity's pointed down, we could evaluate the work, and we would find that the work would just be negative mgh, the work done by gravity. It does not depend on the path. All it depends on is the starting height and the final height, that change of height. And this is an example of it being independent of path. Now, a counterexample would be friction. So non-conservative force would be, consider friction. So imagine situation like think of your top view here, where you have an object and you're going to move it. Say it's an object sitting on a table in front of you. If you slide that object just directly across, versus if you were to slide that object away from you and around and across, the work done by friction here and the work done by friction here is not going to be the same, because it depends on the path that's taken. So friction is not conservative. And actually, I have a little chart in here from your text, I can plop in here. It gives you some examples of conservative and non-conservative forces. Some of these we haven't encountered yet, like the electric force, which you'll get in your next physics course. But like I mentioned above, the gravitational force is going to be the really important one for us in terms of a conservative force. Let me give you another way to think about this distinction between conservative and non-conservative forces. So another definition of this is, so a force is conservative if the net work done by the force on an object moving around any closed path is zero. So if we're thinking about this path picture, if you think about gravity, and what's your deal? So let's compare our two examples again. If we look at gravity, if you start somewhere, say, you go up and you go across and you come back to where you started, you're doing negative work. Gravity's doing negative work as you're going up. It's doing positive work as you're going back. But since you're going back to the same point, the net work is equal to 0. Versus, consider friction again. Now we're talking about a top view. If you start at some location and you go back and you make a loop, imagine dragging an item around on a table in front of you, and you trace out a loop. The work done by friction is not equal to 0. It doesn't cancel out. It's positive all the way around. Friction is doing work the whole time. So this can be another way of thinking about this distinction between conservative and non-conservative forces. So non-conservative, conservative. Basically, if you make a loop with a conservative force, the network will be 0. If you make a loop with a non-conservative force, it won't. It's going to have some value. All right, so this may seem like kind of a tedious, slow discussion, but why we care about this. So this was all section 8.1. And why we care about this is that it motivates section 8.2, which is potential energy. Basically, potential energy is only defined for conservative forces. So, okay. So what is potential energy? So just a note, I'll use PE to indicate potential energy a lot of times because I think it's pretty straightforward what that means. Sometimes your book will use U for potential energy as well. So what is it? It's energy that's stored. I suspect if you've taken any physics, this is an idea that you run into. So it's stored energy. It can be stored in position. It could be just stored in a configuration of charge. It's basically the stored capacity to do work. To kind of connect to what we did in the last chapter. This idea that it's stored being the main thing. So, and again, our kind of go-to example is gravity. So if you imagine, and you probably know this kind of intuitively. If you have an object that's like at the top of a cliff or something, you have a sense that that object has energy that's stored in its position because of gravity. So the only thing that remains is for us to define it. And how we find the change in potential energy is that it will be the negative work done by a conservative force. So with our gravity example here, this is in general F dot dl. But we know that in this picture, so let's put our forces in here. Force of gravity points down. In this situation, our displacement vector would be pointed up, and it would just be up some height h. And if we did this integration, we would find that this is just, negative mgh, the force times that height. And it's negative because the displacement vector and the force of gravity are pointed in opposite directions. And then notice we have this negative sign times a negative sign, so this would equal mgh. So the change in potential energy in this circumstance, if you lift the object, is equal to mgh. It's positive. Um, and this is kind of our archetypal example of uh, of the connection between work and potential energy. So if you have a conservative force, the negative work done by that force is equal to the change in potential energy. And this is kind of the main definition, the main takeaway um, from section 8.2 in chapter 8. So let's look at another really important example, and that's the spring. So really, kind of an excellent system to talk about potential energy is the spring. Um, and is that in our list up here? Yeah, so a spring, something that's elastic. We'll just add it to the list here too. Um, so what's our cartoon for a spring? So we have, a block on a spring, and we imagine, let's say stretch the springs rather. Um, and we know that, if you stretch the spring, it's going to exert a force back, the spring force. And, if we've basically stretched it here in this cartoon from here to here. So that's our displacement vector. And we know that this is going to do negative work because the Frink's force is a restoring force. It's going to be pushing in the, back in the opposite direction of the force that would be stretching the spring. Let's call it the force that's pulling the spring. Um, and so let's apply this definition that we have now, that the change in potential energy is equal to the negative work done by a conservative force. So in this case, it's going to be the spring, and we know that this is one of the essential examples for a force that isn't constant, and so we're going to have to integrate. So this becomes negative integral from, let's say, let's call this position our initial position equaling 0, and then this final position, we'll just call it x final. Um, and so we have our cartoon drawn here in x, and we know that the spring force looks like negative kx. And so what we need to integrate is that, just kx. And we know, or we should know, this integral. Notice our negative signs would cancel, and then we would just have a factor of k times our x squared over 2, evaluated from 0 to x final. And we could put those numbers in. We would have k x final squared, just to be really step by step here, minus 0 if we're assuming that it's the initial position is 0. So this is the potential energy that's stored in a spring. It looks like x squared, actually let me write that cleanly. The potential energy in a spring looks like kx squared over 2. So notice the spring force is negative, but the potential energy is positive because it's the opposite. Or it's not opposite, you have this negative sign. So in other words, if you stretch a spring, the spring is storing positive potential energy. And yeah, like I said, this is a pretty important example and shows you, another situation where we can compute the potential energy by looking at the negative work. So So what have we done so far? We've basically shown some examples how if you know the force, you can get the potential energy by integrating. We know the connection to go from, this vector picture to scalar quantity. And it turns out if you know the potential energy, you can also get the force. So you can also go the other way, which is probably not surprising that there's a sort of complementary relationship here based on what you've learned about calculus. And so what that looks like is this. So if we had to integrate to get the potential energy, it's probably not surprising that you have to take a derivative to get the force. You have to sort of undo that operation. Um, and like I mentioned, there's sort of a complementary nature here. So one detail with this is that to get a scalar out of a vector, the dot product underneath, inside that integral is what converted those vector quantities, force and displacement, into a scalar quantity. So if we're going the other direction, if we're going from a potential energy, a scalar, to a vector, our derivative operation has to impart some direction. So let me show you information. So let me show you what that looks like exactly. So the derivative operation that you do is called the gradient. And what it looks like is this. So it will be a unit vector. So notice this is negative, so these will all be negative. It'll be a unit vector. Actually, let me write it like this. Let's make a big negative sign out in front of everything, times each of the components. So we'll have I hat times the derivative with respect to x, j hat times the derivative with respect to y, k hat times the derivative with respect to z. So a couple notes. U is the letter that your book uses for potential energy. Your text. So just to avoid confusion, these are the same thing. What else? So these partial derivatives, like d dx is a partial derivative. If you haven't encountered this before, that's okay. You will at some point. And you can think of this as basically just take the derivative with respect to x, treat everything else as a constant. So maybe I'll just say here. Treat everything else as a constant. So this is pretty neat. This gives us the connection between potential energy and force. So first, if we know the force, we can look at the negative work and derive the potential energy. Now, if we know the potential energy function, we can find the force. So this lets us go kind of the other direction, which is cool. And let me show you an example of this, a quick example. So suppose your potential energy function, this is just kind of a simple kind of contrived made up example. Suppose your potential energy function looked like x squared y z squared, so this product function. The force due to this potential energy, let's just work it out so we have it kind of in steps so you can see how this works. So it'd be the negative of I hat times the derivative of our function partial with respect to x. Made a mistake. Partial with respect to y plus k hat times the partial with respect to z. And so what do those derivatives look like? Well, this will be negative I hat times the derivative of x squared y z squared with respect to x would just be 2x y z squared. Just treat everything else as if it's a constant. The derivative with respect to y would just be x squared z squared. And the derivative with respect to z would just be 2. We get a factor of 2 from the z squared, so it would be 2x squared y z. And so that would give us the force. That's an expression for the force now. Derived from the potential energy function. So hopefully this helps you see. We'll do some more sophisticated examples with this operation, but hopefully this kind of helps you see this complementary nature between the potential energy and the force, and how we can use calculus to switch between these quantities. And so what have we done in this video? We defined conservative forces. We defined potential energy as being the negative work done by a conservative force. And we also made this connection between, force and potential energy, basically by calculus. And how we can go back and forth, which is kind of neat. So we'll do some more sophisticated examples in class and stuff, but hopefully this gives you kind of some helpful information for the first couple sections of Chapter 8, so sections 8.1 and 8.2.